Today we're going to talk about transfer functions. And we're going to talk about transfer functions for a lot of this semester because these are a big deal in systems. So we talked about how we wanted to have systems where we could talk about an input and an output, and then we talk about the system properties. But in the examples we've handled so far, we've had the inputs included with the system in order to find the outputs. We want to expand our definition so that we can handle any type of input and any type of output and be able to model our systems. And we're going to do that using transfer functions. So this is going to be a way that we can model our system. Later on, we're going to get into state space modeling as well. But transfer functions are going to be the primary way that we model any system. And they have a pretty fancy mathematical definition. And we're going to go with that first, but then we're going to see some properties and some patterns as we explore it throughout the first few weeks of the class. So, by definition, the transfer function is the ratio of the output to input of a system in the Laplace domain, where initial conditions are always set at 0. So, even if you know that your system will not have 0 initial conditions, the transfer function, by definition, always sets those initial conditions to 0, whether or not that's the case. It's part of the definition of a transfer function. Now, there's some interesting properties about transfer functions and the reason that we study them. First off being that transfer function is an inherent property of the system. So if we have a mechanical, electrical, fluid, any type of system, we might have different governing equations or ordinary differential equations depending on how we set up the system. So you might have a different set of equations on your page than your partner or whoever's sitting next to you. But if you then go through and find your transfer function of your system, that's going to be the same regardless of how you set up your equations. So this is an inherent property of the system. And if we have the transfer function and we know what our input is, then that means we can predict what our output will be. If we don't know our transfer function, but we have a way to measure our output, then we can experimentally calculate our transfer functions using known inputs and measuring our outputs. Then, by finding our transfer function, we could then predict any output given by any changed input. So that gives us a lot of power. Because our transfer functions are in the Laplace domain, then we can have them in the format of a numerator over a denominator. And the poles are going to be the solutions of setting our denominator of s equal to 0. So in the example problems we've seen in class so far, the numerator was the only thing that changed, and we're going to see that for systems. So the denominator is pretty much based off of the property of a system. Your poles of your system are going to be set by your transfer function. When we get fancy controllers, we can adjust the poles some more, but that's going to be, the poles are the solutions of setting the denominator of your transfer function equal to 0. And we do that so often that we actually give that equation its own name. So that's called the characteristic equation of the system. And so if you set the denominator of your transfer function equal to 0, that can tell you the poles of the solution. The solutions will be the poles. Your book refers to them as the roots of the equation. We use poles for the most part. And one thing to note is that initial conditions are set to 0 in order to calculate a transfer function. Depending on the more complex systems, we cannot add initial conditions back in. When we go look at time analysis of systems, we're going to find out why that's okay, but I'm just telling you now, we will not be able to add initial conditions back in with transfer functions. Okay. So let's look at an example transfer function using that same mass spring damper that we've been playing with all throughout the semester so far. It's been a week, but it's been a long week. So we have our mass spring damper system. X we've decided is going the same direction as the input force. So X will be our output, input force will be the input. If we wanted to do this from scratch, we would draw our free body diagram, use that free body diagram to sum up the masses in order to get a governing equation of the system. And then if we want to find the transfer function, we're going to take the Laplace transform of this equation, and we're going to say that all initial conditions are equal to 0. So instead of having x double dot in the Laplace domain as s squared x of s minus s x of 0 minus x dot of 0, we're just going to say that it's x double dot becomes s squared times x of s. So the math gets really easy when we set our initial conditions equal to 0, because we're just going to have an s for each derivative, and we don't have to consider any initial conditions. Now, Laplace transform, we need to, for the transfer function, we need to take the Laplace transform, we need to set initial conditions to 0, which we've done that, and now we need a ratio of the output over the input. So our input is our force, and our output is our displacement, x. So we want to isolate our input and output in order to get our transfer function. So we'll put all of our x of s terms on one side, and our f of s terms on the other side, and then we're just going to have that since the transfer function is the output over the input, we're mathematically going to have x of s over f of s, and manipulating this equation, we get that that is equal to 1 over ms squared plus cs plus k. So that is our first transfer function. It is by no means our last transfer function, but we're going to be using them a lot in class, because once we have transfer functions, we can figure out how our system will respond. We're going to learn a lot about the behavior of a system, and be able to work with experiments, with testing. So for now, we're saying that we can find the transfer function, and using MATLAB, which we're going to do a little bit in this class, we're going to be able to put some inputs back into our system. So this is a way to isolate our system before there's any inputs or initial conditions. We can't put initial conditions back in, we can put inputs in. So just for our reference, we're going to talk about a couple different inputs. So in class, we've already seen an impulse. So an impulse is where we say that there's some yank or sudden adjustment, and so that's considered delta t, which is, we can say that our input goes up to a value, and we have time as our x-axis. Our y-axis, I didn't put a unit because it depends on what type of system we have. So we have some input that would go up to a value of 1, and I think actually the mathematical definition of an impulse is that it goes to a value of infinity, but the area under the curve is a value of 1. We just consider it a yank. A more common one is going to be a step function. So that's where we do not have an input, and then the input is adjusted to some common valve. So we can think of this as turning on a switch in a circuit, or turning on a faucet in a fluid system, or adding a weight to a system in a mechanical system. That's a step function. Ramp function, we use less of an example in this class, but that's also a kind of common one in systems equations. But in reality, even though these are the mathematical ones we see a lot, an input can be whatever we want it to be. So we might have a sine function, a cosine function. We're going to have an example where we look at a heartbeat as the input, because we're trying to measure what's the pressure in someone's heart. Any function you want can be a possible input. It doesn't have to be as simple as an impulse or step. We're just going to start off with those in the beginning of the class. Okay, so that's it for this video.